Suppose I gave you a problem where I wanted you to find the maximum area of this enclosed region. And we can see that when we're talking about area, we know that it's going to be length times width. So let's just label this as my length, and we'll say that our width is this. And if we wanted to write this as a function, we'd say that the area of this function then would have to be length times width. So in other words, 4x times negative x plus 2. And we can actually clean this up here. We can say that this is negative 8x squared plus 8x. So it's a pretty straightforward quadratic function. So if I wanted to find the maximum area that would be possible, I want to know when that, first off, when that maximum area is going to occur. What would the dimensions have to be? Specifically, what is the x value such that I'm going to get the length and the width that will produce the maximum area here? Well, if we're looking at this function here, we notice that it's quadratic, and I then want to find the maximum output of this quadratic function. It would then make sense that I would want to find its vertex. And if that's a little bit hard to grasp, let me just pull up that graph here. And I went ahead and I just graphed this function. Actually, let me just go ahead and change it so that it's 8x. Okay. Oh, you know what? I realized I made a mistake. This should have been negative 4x squared. I apologize. Sorry about that. Got too a little ahead of myself. So it should be negative 4x squared plus 8x. All right, so I think we're all straightened out now. So if this were my function here, and I want to see the maximum value of this quadratic function, I would simply be trying to identify the vertex, which graphically I can see here is going to be the point 1, 4. So let me actually zoom in on that, 1, 4. And I can also find the vertex, which I know is going to be where the maximum is occurring by finding negative b over 2a and evaluating this same function at negative b over 2a. And in this particular case, I would see that it's the point 1, 4. And we learned how to do that in pre-calculus and algebra 2 by finding the vertex of a quadratic function. So then the question then begs, how would we do this if we were dealing with a non-quadratic function? How could we find the points or the values for our independent variable that will produce a possible maximum or a minimum? Well, if you think about it, we've already talked about in this course how to find maximums and minimums. We found how to find relative extrema using both the first and the second derivative. So that's essentially what we're doing in this lesson, but we're going to be doing them in context. So today's lesson is all about optimization. It's essentially this process where we're going to be trying to find the possible parameters that will create a maximum or minimum output for a given situation. And in order for us to do this, there are going to be a couple of situations or conditions that we're going to need to consider. The first thing, we were going to want to come up with, and I'm going to highlight it because it's super important, an explicit equation that relates the wanted variables. And oftentimes what that means is we're going to have to come up with a secondary equation that allow us to substitute in case that we have too many variables. We want to write all of our explicit equations in as a function of just one independent variable. We're also going to need to think about possible domains in the context of the problem, right? So oftentimes that means we won't want negative time or an unlimited or infinite time or an infinite parameter. Sometimes there are certain conditions that we are restraining ourselves to. And then the final thing is for us to think about the first derivative and the second derivative test for finding maximums and minimums. So let's try this particular problem here, and then we'll ask ourselves some of these same questions as we go along. So the problem is as such. We have 48 squared centimeters of cardboard to make a box that has no top, so it's an open box. We're also told that the box must have a square base. What dimensions will give us a maximum volume? So in this case, I've drawn the figure for you. Oftentimes you may need to do this yourself, but I did it just to remind ourselves that the base must have a square base, or must be square. So if our width here is represented by W, that means its length is also going to be W. So I'm going to just quickly write that there, that our length is also equal to our width. And then we have the height, which we're not told any specific information about, but we will be able to connect our height and width in just a moment. All right, so given this information, let's ask ourselves, what parameters are involved here? Well, we know we have length, width, and height. Well, we know that if our base is a square, that our length has to be equal to our width. We also know that our height we'll be able to write in terms of our width in just a moment. And then finally, are there any other variables that we might want to consider? Well, not any new variables, but we do want to keep in mind that since we are finding the volume here, the maximum volume, we're going to want to say length times width times height produces the volume, or finds us the volume. And since, again, length is equal to width, we can say our volume is equal to W squared times H. So it's just W times W. All right. Is there any other information from this problem that we can use to write the equations? Well, if we look at the problem carefully again, we're also told the amount of cardboard that we're given here. This would be our surface area. Let me just write that, our surface area. Well, ask ourselves, how do we find surface area? Well, I know it's going to be the area of our base, which in this case, again, is W squared. That's the area of our base, plus the area of each one of our sides. So we initially found the area of our base, which is this here. I'm just going to kind of highlight, color that in, just represent that as W. And then we're also going to find the area, let me just do this in a different color, of each of our sides. So one of these sides here. And we have 4 of these. So we're going to have 4 of these sides which have an area of W times H. So 4WH. Okay. And when we add up all of these areas, we're going to get 48. We're told that we have 48 squared centimeters. Now, looking at this now, can we figure out a way to isolate H or write H in terms of W? And we do. We can say 4WH is equal to 48 minus W squared, and H is equal to 48 minus W squared over 4W. So now that we've done that, we've kind of really accomplished this step right here, a secondary equation that allows us to do our substitution. Now we can write our entire function of volume in terms of just our independent variable, which is W. W is our independent variable. Our dependent variable is V because we're trying to solve for the volume. That is to say, volume is going to be dependent on whatever our W or our width is. So now that we all have all that, let's go ahead and start trying to find that maximum volume. Again, we know that volume, and actually, you know what? Let me write this as a function. Well, let me do this first. We know our volume is going to be W squared times H. Volume as a function of W is going to be W squared times, what do we say H was? H was 48 minus W squared over 4W. So 48 minus W squared over 4W. Let's clean this up a little bit. That's going to give me 12W minus W cubed over 4. And now that we have this is our volume function. So this is the function that gives us the volume of this particular box. Now let's think about the domain real quick. Let's think about the domain of this function. That is to say, are there any conditions for what we can plug in for W? Well, what's the lowest value that W could be? Well, it's got to be greater than 0. We know that because if our width is equal to 0, we no longer have an actual box. Now, pause and ask yourself, well, what's the maximum that our width could be? Well, we know that the maximum has to be the square root of 48 because we know that the amount of cardboard that we have is 48 squared centimeters. So if we use all of our cardboard just to make the base, if this was 48 centimeters squared, which it's not, then we would just have a flat base. We would use all of our cardboard for that base and there would be no sides. So we know it's got to be less than the square root of 48 because W times W is equal to 48 in this particular example. Okay, so we know that that is not the case. So I'm gonna actually go back here and get rid of that 48 centimeters squared. So we know that our width has to be must be less than the square root of 48. So now that we have all that, let's go ahead and let's differentiate our volume function. So V prime, I should say, will be 12 minus, in this case, 3/4 W squared. Now, what are we doing? We are using the first derivative test now to see if we can find the values for W that will produce a relative extrema. We're going to set our derivative equal to 0. So that's 12 minus 3/4 W squared. So we can say 3/4 W squared is equal to 12. Multiply both sides by 4/3. W squared would then be equal to 16, which means W could be equal to -4 and +4. Again, if we think about this in the context of our domain, we said that our W must be non-negative. So we are going to disregard -4 as a possible option. So far, we can say that one of our critical numbers, W, is equal to 4. Now, just because something is a critical number doesn't mean it's an extrema. So now I'm going to draw my W prime number line. Again, at 0 and root 48. These are kind of conditions for our domain, for our W. And we're going to put 4 here. And we're just going to apply the first derivative. We're going to check our first derivative. We're going to plug in values to see if our function is increasing or decreasing. If I try plugging in a number like 1, something that's in between 0 and 4, if I plug 1 into my derivative, we're clearly going to get a positive number. If I plug in a number greater than 4, let's say, for example, 6, we can see that we're subtracting more than we have as a constant of 12. So this is going to be negative. So we go from increasing to decreasing here. And based on what we know about our first derivative, we can then establish that W is equal to 4. This is going to represent where our relative max is. Well, if that's where our relative max is, then let's find the h value when W is equal to 4. So we know our maximum occurs when W is equal to 4. So now let's plug 4 into our function. So if we plug 4 into our function here for W, going back into this step here, we're going to then get, oh, sorry, not into that function, I apologize, for h. We want to plug it in for h. So when W is equal to 4 here, that's going to give us, so h of 4, it's going to give us 32 over 16, which is just 2. So our height then is 2. So we've established that we're able to get the maximum volume when the width is equal to 4 and the height is equal to 2. And so let's write this as a sentence. We have a max volume when the width is equal to 4 centimeters, we need our units, and height is 2 centimeters. Okay, so this is a good example of an optimization problem where we're able to find the maximum volume using what we know about the first derivative. Let me do one more type of problem with you before I finish up this video, but let's try something like this next example here. We're told that the sum of two non-negative numbers is 30. Find both numbers if the sum of twice the first plus the square of the second number is a maximum. And then do the same thing if all of that is a minimum. Okay, so that sounds like a lot. Let's break this down. First off, let's define our two numbers. Let's let x be our first number. And then let's let y be our second number. Okay, all right. We know that the sum of these two non-negative numbers is 30. So we're going to say x plus y is equal to 30. Now, let's try to make sense of this next sentence. The sum of twice the first, so the sum of twice the first, so the sum of, so since we're finding the sum, we're going to say the sum twice the first number plus the square of the second number. So that would be y squared. All right. Now, we've got two different variables here. We're going to need to see if we can write one variable in terms of the other. And so from here, it doesn't really matter which one you choose, but I'm going to just rewrite now y as being 30 minus x. I'm writing y as a function of x. So I'm going to do that substitution. I'm going to say, now our sum is 2x plus y as a function of x, so 30 minus x, that quantity squared. Okay, so now let's clean this up a little bit. We can say that this is 2x plus 90 minus 60x plus x squared. And if we write this in descending order, this would be x squared minus 58x plus 900. All right. Now, so that is our sum function. That's the function that's going to give us a sum. So we know that we're going to need to find the derivative of this. Before I do, let's establish the domain. What do we know about the domain of this function? Well, actually, let me write it here. We know that the domain of this function, we're going to be inputting values of x We know that they have to be non-negative. So in other words, it's got to be greater than or equal to 0, meaning 0 is a candidate. It's a possibility. And since the sum of the two numbers is 30, we know that the largest value that one of the numbers could be 30. Like potentially we could have 30 and 0 as our two numbers. Now let's go ahead and let's find the derivative. So s prime. So the derivative of our sum function is going to be 2x minus 58. We're going to set this equal to 0. 2x then is equal to 58. X is equal to 29. That's our critical number. But we don't know it's an extrema until we actually see if there's a sign change. So I'm going to put my number line here. And in fact, let me actually make this somewhat more accurate. We know the lowest number is 0. The largest possible number is 30. Plug in any number that's less than 29 now. Let's try something like 1. So that's going to give us a negative value. So it's decreasing here. And you can kind of see here, if we plug in a number that's going to be greater than 29, like 29.5, it's still going to, that value is going to be greater than twice 29. So that's going to be a positive value. So this function goes decreasing to increasing here. So we can see here that 29 represents a relative minimum. So let's actually jump to doing part B first. Let's actually do part B first. We're going to say, when we're looking at a minimum, if it's a minimum, we know then that our first number, x, is 29. Okay? Because we know that a minimum occurs when our first number is 29, when x is 29. If the first number is 29, then clearly the second number, y, has got to be 1, because the sum of these two numbers has to be equal to 30. Now, what about if we're looking then at a maximum? Well, we can see from our first derivative that there's no maximum here. We didn't find a relative maximum. So then we have to consider then the endpoints here to see where there might be a maximum by looking at absolute maximum here. Well, in this case, it doesn't really matter which is which, but we can say when our first number is 0, then our second number is going to be equal to 30, right? And when our first number is equal to 0, then that means this is 0, this is 0, and then our maximum here, we could say that s of 0 is equal to 900. So that is the maximum sum that we can get here. The maximum sum will occur when our first number is 0 and the second number is 30. So hopefully this helps give you a sense of how to set up optimization questions and really just making sure that we are able to find a function in terms of our independent variable.